Hello everybody, Happy New Year and welcome to our second video. This video is regarding voice over LTE, and in this video we will discuss basically have an overview of voice over LTE. The video has been divided into two parts, as you can see on the whiteboard. First is the fundamentals and then is the architecture. In the fundamentals part, basically the understanding that we need to develop is that voice over LTE is a major shift from the circuit switched voice services to packet switched voice services. So in the legacy networks like 2G and 3G, all the voice services have been provided with circuit switched topology, while in LTE, as you all know, LTE is an all IP network. So voice over LTE gives us the capability to provide packet switch voice. So that means that this is an all LTE operation. So there is no need for a CS fallback to a legacy network. Voice services and even video services and rich communication services can be provided via the LTE network. The third part is the additional protocols. So these are the additional protocols that have been you can say overlaid on the LTE physical layer so that we can perform the voice over LTE. These protocols include SIP, RTP, RTCP, XCAP. So we will discuss those protocols in our video. Now the second part is the architecture. So what are the network nodes that we basically would be requiring to have voice over LTE in our network? The first part is IMS. So IMS is the IP multimedia subsystem. This is the major you can say upgrade to an LTE network that we require to have the voice over LTE services. Then even in the physical LTE network, that is the radio network, we have to have guaranteed bitrate radio bearers. Because voice has its own requirements in terms of packet loss, in terms of jitter, in terms of delay. So we have to have guaranteed bitrate radio bearers. The third part is the QoS. QoS is extremely important for voice services to maintain user satisfaction. And this QoS is implemented by the LTE physical layer, by the QCI, and also by the IMS in terms of packet segmentation, in terms of packet loss, and in terms of how the packets are being delivered. And then there are the issues. So voice over LTE has some issues that get generated in the general LTE radio part. So we will discuss those issues as well. So I will give you a brief overview in this video, and there will be some details about the radio part and some details about the IMS part. So let's now move towards slides. Let's begin by viewing voice over LTE in a nutshell. Basically, voice over LTE is the evolution of legacy voice service in the cellular networks. Before 4G and LTE, voice services were provided through circuit switch technology. In the initial phase of LTE deployment, CS fallback was extensively used to provide voice telephoning while you're on the LTE network. Of course, in CS fallback, as we discussed, we have to move to the legacy networks, that is the 2G and the 3G networks. Circuit switch technology, as known by many of you, reserves that particular channel for the independent usage of that user, and therefore it is not to be used in kind of a shared spectrum or a shared channel. With voice over LTE, the voice and video services have been delivered using packet switch technology, which is a lot more bandwidth efficient, and like any other IP packet can be scheduled on the shared channel. Of course, as we will discuss, the QoS requirements are different for voice over LTE as compared to some novel data traffic. Voice over LTE is delivered via a combination of LTE radio network and IMS, that is the IP multimedia subsystem. There are of course other nodes involved in this as well, but primarily it is the co-working of LTE radio part and IMS to provide packet-based voice telephony. Let's look at the bulleted points now. Voice and video call services have been using LTE radio network and IMS. That is the core concept of voice over LTE. It is, as explained, evolution of the CS-based voice service to the PS-based voice service. And voice over LTE is the complete IP-based solution for voice and video service. And of course, the QoS requirements are different for voice and for video. As you might have seen in your mobiles, there comes a sign of HD. So this is HD voice calls using guaranteed bitrate QoS LTE profile. There is no requirement now for the UE to move to legacy network for voice services, and therefore while you're having your voice services, all of your data bearer can remain on LTE. Radio and IMS core architecture is involved in setting up and making a voice over LTE call. And as we will now discuss in the next slides, there is an IMS architecture, there is LTE radio architecture, and then there is your interplay. Let's move to the next slide now. In this slide, we're basically going over the general architecture of voice over LTE and how it is handled in the LTE network. Voice over LTE in terms of the network layers is a combination of SIP, XCAP, RTP, RTCP overlay on the radio layer. So SIP is basically used for the communication between the user and the IMS server. Proxy CSCF and the VoLTE functionality in IMS is handled via the SIP functionality. SIP is basically your session session initiation protocol. We will discuss it in the next slide. RTP is used for transmission of actual payload, that is the voice IP packets. RTCP is used for the control for the payload configuration, for example the block size, the error, and etc. IP packets are delivered using LTE radio bearers with corresponding QoS profiles. Compression, scheduling, and other techniques are used to handle voice specific bearers in LTE. If you look at VoLTE in a nutshell, in terms of technical implementation, voice over LTE involves a number of new protocols introduced in LTE to ensure QoS and required KPIs for the voice traffic. As you can see in the figure on the right, there are three network functions on top of the LTE bearers and the physical layer. Some of these protocols are namely SIP, XCAP, RTP, RTCP. The most talked about protocol used in voice over LTE is the session initiation protocol. And since a lot of overhead is added in terms of the additional protocols, compression techniques are used to improve network capacity. Voice over LTE also poses issue for the control channel capacity in LTE, and scheduling techniques and some other techniques are also used to counter that. Now let's move to the next slide where we will discuss the IMS functionality. In this slide, we will discuss the IMS functionality. In LTE, IMS, your IP multimedia subsystem, handles the session initiation, payload transfer of the IP packets, session and NQoS handling of the data traffic for the voice over LTE. We have SIP. This protocol is used for establishing the connection between the UE and IMS, and also between the two UEs for the voice over LTE call. It has to be noted that SIP is not used for the actual transmission of the voice packets. Codec, bandwidth, transport form negotiations are performed between the two voice over LTE users using the SIP. This is the same case if one of the calling party is voice over LTE and the other is in a PSTN or a CS fallback call. RTP and RTCP are used for actual transmission of the payload, and IMS would require the SIP proxy server, media gateway, voice over IP application server, and also a centralized CSCF and HSS for the entire functionality of the voice over LTE call. Of course, it is also obvious from the figure on the right that the IMS will have a link towards the PCRF, and through the PCRF to the packet gateway and the SGW that is to get the QoS profiles and then get to the radio LTE radio bearers. Just to add a bit of explanation for SIP. SIP stands for the Session Initiation Protocol. SIP is used for the connection establishment between the UE and the IMS. It consists of messages such as invite, status OK, ringing, session in progress, etc. SIP is used for setting up the codec, bandwidth, transport block format, and other required session parameters, and these are negotiated between the two calling parties before sending any voice packets towards each other. when the and when the first UE, when the UE for the first time attaches to the network, it provides the information about its voice over LTE capability. The network then basically attaches the mobile first to the LTE network and then to the IMS. In the network attach message, proxy CSCF IP address is provided, which is then used by the UE to gain I-CSCF and the serving CSCF once the UE tries to make voice over LTE call. The RTP protocol, which is basically a real-time transmission protocol, is used for the transmission of actual voice packets. And RTCP is basically a protocol used to control the parameters and performance of RTP. The packet headers are added with each protocol, and then these IP packets are delivered by the LTE radio network through the radio bearers. Now we will have a look at the radio network functionality of voice over LTE. In this slide, we will discuss the radio network functionality of voice over LTE. In LTE, all traffic is categorized into a bearer profile. So once we have to map the physical LTE channels onto a physical bearer, we have to give it a profile. Upper layer protocols are not visible to the LTE physical layer, so whatever is happening on the SIP layer or on the RTP layer or the RTCP layer, that will just be as a data packet that needs to be delivered. But QCI based profiling will be done for voice over LTE traffic. QCI1 is used for voice packets, and that is basically the bearer that will be used for all voice over LTE packets. Then QCI2 is used for video packets, and QCI5 is used for SIP messages. All of these QCI for the bearers are guaranteed bitrate bearers because of the sensitive requirements of voice and video. The minimum configuration that is required for on the radio part for in terms of bearer is 2 signaling radio bearers, 2 acknowledge mode dedicated radio bearers, and 1 unacknowledged mode dedicated radio bearer. The bearers are then mapped to specific LTE physical channels. The packet gateway takes the QoS profile from the PCRF and then instructs the MEME to provide the required bearer. Now we will explain it a bit further. All IP packets, including the one used for SIP signaling and the ones containing actual payload, have to be mapped onto the LTE bearers for transmission on the LTE radio network. In LTE, the QoS differentiator is QCI, which takes input in terms of bitrate, MCS, and scheduling. Voice over LTE, due to its stringent requirements on delay, jitter, and packet loss, is assigned QCIs of 1, 2, and 5. QCI5 being primarily used as a default IMS bearer. In the attach phase, when the first time UE accesses the network, it informs the network about its VoLTE and IMS capability. The network then first attaches the default acknowledge mode bearer QCI 8 or 9 and then goes to establish the IMS bearer for SIP signaling QCI 5. Once the bearer is established and the UE registered in IMS via the proxy CSCF IP address provided by the attach procedure, the UE is then ready for the HT call, and we can see the voice over LTE symbol on our mobiles. The minimum configuration includes the default dedicated radio bearer QCI 8 or 9. Then we have the default IMS bearer QCI 5, and then we have the voice over LTE data bearer that is QCI1 and QCI2. It has to be highlighted here that QCI 8 and 9 and 5 are in the acknowledged mode, and these are basically the default bearers. The bearer which is used for delivering the video packets or the voice packets is used in the unacknowledged mode, and that is to avoid unnecessary delays in the retransmission. You can see in the right side, you can see the APS bearer and how basically it is divided into a radio bearer and then into an S1 bearer and then into S5/S8 bearer. When the UE goes into an idle mode, only the S5 and S8 bearer is available, and whenever there's a connection ROC configuration request, then we can establish the radio bearer and the S1 bearer again. Now we will move to the next slide, where we will basically have a brief summary of the major issues that we can see in the network for voice over LTE. Now let's look at the major network issues that may arise with the deployment of voice over LTE or with the ongoing performance of voice over LTE. Whenever voice over LTE is deployed in a network, the most foremost and the most prevalent problem is the extra load on the PDCCH. As you know that in LTE we have the physical downlink shared channel, and in order to use the resources of the channel, each user is given a grant, and the grant notification is sent on the PDCCH. However, the profile of the data for the voice is very different, and it requires consistent grants to be made to that particular user. So if PDCCH is used to provide dynamic scheduling grants to the voice over LTE users, the PDCCH gets congested, and therefore the other users which are not a guaranteed bitrate users, for example they are QCI 8 or QCI 9, they won't be actually scheduled, and therefore we can have a situation where basically only the voice over LTE users are being scheduled, and the throughput for the other users, which are only the data users, goes seriously down. To counter this issue, there are some scheduling schemes that we are used. One of this is called the semi-persistent scheduling scheme, which is basically used to avoid PDCCH load. Then we also have segmentation, we also have TTI bundling, and of course we cannot go into the detail, but I will probably giving us another lecture on the optimization issues for voice over LTE. Then we have the sensitive delay budget requirements, that is the packet delay budget requirements for LTE, for voice over LTE, and the planning has to be catered for that particular delay budget, because when you're talking about streaming, you're talking about normal uploads, downloads, it does not have that stringent requirements of packet delay. But when you come to voice over LTE, the requirements are very stringent. So we have to basically link budget the cell edge users according to the delay requirements of voice over LTE. So as you can basically the basic requirement, that is the mouth to ear delay, that is one party speaks from the mouth and when it reaches the ear of the other party, so the delay is usually 200 to 280 milliseconds, that is acceptable. For 200 it is very good, and for 280 it is acceptable. Anything later than that, the user will observe it, and of course your MOS score, your user perception, everything will go down from there. Then we have the intra LTE handover issues and the SRVCC. For intra LTE handover, we have basically a different type of issues. For example, the data forwarding on the X2 interface that has to cater for the particular delay that may incur for that. Then we have different hysteresis introduced for different handovers that are voice over LTE specific. So when you're optimizing the network, you can have basic optimization parameters which are voice over LTE specific. And when you talk about voice over LTE specific, it means that they are QCI specific. So you can set up hysteresis for QCI 5, you can set up hysteresis for QCI 1, etc, etc. For SRVCC, this is also, there are parameters that ensures that we have call connectivity. And then we have the network performance KPIs that will basically, we can get the KPIs from the OSS. Then we have the KPIs from the drive testing teams. Then we have KPIs from call traces. And the troubleshooting of voice over LTE basically involves all of those KPIs. And the major KPI is the delay, and then you have your normal KPIs of retainability, accessibility, and your handover success rate. And then you have your jitter KPI, your MOS, and etc, etc. So this was a brief overview of voice over LTE, and now let's move to the conclusion. Thank you guys for watching the video, and I hope that this brief overview would help you understand voice over LTE, and will also help you in understanding how voice over LTE functions in the LTE network. If you have any questions, any queries, feel free to drop in the comment section, and also you can contact us in the contact details given in the video details. And if you have any requirements in terms of any knowledge sharing, any trainings, any consulting, please feel free to contact us. Thank you.